Can throw them in the chat box as we go along, and I'll try to check that periodically. I'm born and raised in Lower Michigan. I've focused on atmospheric and climate science as my research and teaching area over the years. I've taught at Oakland Community College, Central Michigan University, Saginaw Valley State. I was assistant professor at Northland College for 2 years before being offered a position. It's kind of a joint position in academic advising and teaching back at my previous department of geography, environment, and spatial science at Michigan State. Most of the figures I'm going to be showing you today is coming from a single textbook. This is a book that I'm going to be using for my course on people and environment, starting here in the spring semester. This is by Andrew Dessler on modern climate change, which is the focus of our conversation today. I've kind of broken this lecture into three roughly equal parts. We're going to be looking at climate change symptoms, science, and potential solutions going forward. So to get us started here, we're going to kind of go back in time in Earth's history over about the last 65 million years. Present day is on the right-hand side of this figure. I am going to be showing temperature mostly in Celsius degrees with these figures today. And this is looking at Earth's average global temperature over the 65 million years. And very quickly, we can see that the overall trend has actually been decreasing temperature over most of that time. You see that rapid spike in temperature there about 55 million years ago. That's the Paleocene, Eocene thermal maximum. This occurred after the impact with Earth that's thought to be the leading reason for the extinction of the dinosaurs. Perhaps volcanic activity and wildfires after that event and the release of carbon dioxide from that is what's responsible for that rapid spike in temperature. And then we had the Eocene thermal optimum there around 50 million years ago, and then temperatures have generally declined since that time, bringing us to the present day. And you see that shaded area on the right-hand side showing us the last 4 million years. We're going to zoom into that here in just a second. Now, how do we know the temperature that we can display on a figure like this? I mean, certainly these values are largely preceding thermometer technology that we have today. So we didn't actually have these temperature readings from all these millions of years ago. So these are our best estimates, and it's based on what nature provides to us. We can rely on various symptoms from nature. In this case, it's primarily from ocean sediment cores. We look specifically at oxygen isotopes, the ratio between O16 and O18, and it's an analogous method for estimating temperature. When O18 has a higher value in that ratio, it tells us that temperatures were warmer during that period of time. Okay, so let's take a look at the last 4 million years. We can now start to see more variability in temperature over this time period. See the variability increasing as we approach the present day. The approximate time between each peak and bottom of each one of these squiggles was historically around 41,000 years. And then in the last several of these cycles, it's been closer to 100,000 or so years. But there is some amount of repetition, and we can see that rapid increases in temperature followed by relatively rapid decreases in temperature have been the norm throughout Earth's history. Again, this is largely from ocean sediment cores relying on oxygen isotopes for estimating the temperature. But if we take a look at the right-hand side, the last 400,000 years, we can see the last 4 or 5 of these cycles. And you can see that it was rapid warming followed by a little bit more gradual cooling, and then rapid warming, gradual cooling. And that has repeated about 5 times there that you can see in that gray shaded area, the last 400 or so thousand years. So we're going to take a closer look at that now. Temperature is the solid black line again. We can better see the rapid warming followed by gradual cooling. It's repeated 5 times on this figure. Present day is on the right-hand side, and we reside at the top of one of those warm peaks. If this evidence here suggests anything to us, it's that we can probably anticipate another gradual cooling trend that will ensue over the next roughly 100,000 years, followed by another period of rapid warming. The other piece of information that we've now included on this figure as the dotted line is carbon dioxide concentration in the atmosphere. This is an important atmospheric constituent because it behaves as a greenhouse gas. We're going to talk about that in a few moments. Concentration here is in parts per million. So if you imagine taking a sample of air and dividing it into 1 million parts, count the number of those parts that is made of carbon dioxide. We should expect it today to be somewhere around 400 parts per million off the top of the graph that we see here. Historically, in recent years, the values range between 260 and 280, and that's what you see at the top of the graph here. But you can certainly see in periods where it's been cooler, it's been more like 180 parts per million. You should be able to see that the relationship between carbon dioxide concentration in the atmosphere and global temperature is very strongly correlated. When greenhouse gas concentration is higher, temperature is also higher. Let's take a look at that most recent spike in temperature. We refer to this as the Holocene Epoch, and that is on the right-hand side of the figure. So this is the last about 11,000 years. And we can see that temperature started warming about 11,000 years ago, plateaued in warm temperatures from about 10,000 years ago until about 5,000 years ago, and then started cooling. And in the last couple hundred years, we see a very rapid warming that closely corresponds to our industrial revolution on a global scale. We're using temperature anomalies here, so it's a difference from a long-term mean, and the long-term mean that we're using is 1961 to 1990. We usually use a long-term mean of at least 30 years as a baseline. Next figure, let's take a look at just the top part of this first. This is looking at average global temperature over the last about 140 years, dating back to 1880. So this is from our actual thermometer record. We have removed the annual seasonal cycle so that we can remove some of the regular noisiness from the temperature record. So with the annual seasons removed, we have the thin gray line on that figure. So you can see the ups and downs. There's definitely variability from year to year. Some years warmer, some years cooler. A lot of that year-to-year variability has to do with the presence of either an El Nino or La Nina present. To help pinpoint the overall trends a little bit better, we also provide a 5-year smooth line. Again, using temperature anomalies here. In this case, it's using a baseline of 1951 to 1980. Overall trends that we can see is that temperature cooled from 1880 until about 1910, and then temperatures warmed from about 1910 until about 1940. And then there was a period of stagnant temperatures from 1940 to about 1970, and temperatures have been warming since the 1970s. If you look at it as an overall trend on a first order, certainly we can see that the global temperatures warmed over that time. It is a bit of a mistake for us to use the term global warming, in my opinion, just because there's not consistent warming across the entire time period. There's variability between years. There's variability between specific locations. So I think a mistake people sometimes make when they think about global warming is they assume that all locations are warming all the time, which is not the case. That's why climate change is perhaps a better term for us to rely on. To show some of the regional variability, we can now look at the bottom part of the figure. We split this into 3 different latitude ranges. 24 to 90 degrees north is going to be a northern hemisphere representation. That's the thin black line. Southern hemisphere is going to be the the bold dash line from 24 to 90 degrees south. And then the tropical latitudes near the equator is going to be the dotted line between 24 degrees north and south latitude. We can see that the overall trends for all three regions is roughly the same, but the magnitude of warming and cooling does vary. Northern hemisphere in particular has experienced the greatest amount of warming, both in the middle part of the 20th century and also here in the most recent decades. And one of the leading reasons for that is that the northern and southern hemispheres are very different in terms of their land to water contrast. There's a lot more land mass in the north, much less land present in the southern hemisphere. Land and water warm and cool at different rates. They have different heat capacities. Land tends to warm more rapidly, and we can easily see that here in these last couple decades. This is also in the northern hemisphere. In high latitudes, we tend to see the greatest rates of ice loss. We're going to show you that here in a few moments. Now, Earth is mostly covered by water, about 70%. If we look at ocean by volume, we can sample ocean at various depths and look at its temperature. At great depths, the ocean temperature doesn't vary all that much. Most of the change in temperature is going to be at the ocean surface. But if we average the entire volume of ocean with the instrumentation that we have, we can still see that ocean water is increasing in temperature. It's not a large value, the small decimal value here, but it has been increasing, especially since the mid-1970s. Okay, so we know that Earth's land surface is warming. We know that the ocean is also warming. Ocean is warmed not very much, but the ocean has a large volume. It stores an enormous amount of energy. So even a small increase in ocean temperature is going to have a big impact on Earth's overall climate. With these warming temperatures, we should expect the present quantity of ice to start melting, and we can observe this and display it in several different ways. We're looking at mean glacier length in this first figure. We split it into 5 different regions that you can see represented on the figure. This is looking at the last 300 years. The values here are relative to their length in 1950. And we can see that glacier length didn't change that much for the first 150 years or so, but corresponding to warming temperatures and the Industrial Revolution, you can kind of see that things very rapidly started changing around the year 1850. Mean glacier length started decreasing rapidly, not just in some regions, but really all regions of the Earth, both northern and southern hemispheres. With the addition of satellite imagery in the 1970s, we can now really start to better monitor the presence of ice on Earth's surface. The easiest variable for us to look at is the area, or the 2 dimensions of ice on Earth's surface. So this figure doesn't capture the thickness or the 3-dimensional volume of ice, but it's just giving us the area. The units here are in millions of square kilometers. And we're specifically looking at the Arctic Circle, and this value is collected in September of each year, which is around the time of minimum ice coverage in the Arctic. And so we start in the late 1970s when we have around 7.5 million square kilometers of ice present at that time. And you can see just how quickly this acceleration of ice loss has taken off over the last couple decades in particular. There is a lot of variability between year to year as we've had cold years and warm years, but do note that it doesn't go down to 0 on the vertical axis. So it's not like this value is approaching 0. We still have somewhere between 3.5 and 5 million square kilometers present in these later years, but the trend has been steadily on a decline. I'm just checking the chat box here. Lisa's asking, does it also relate to industrial settings? I'm not sure what you mean by settings. The industrial type or energy type is perhaps what I'm assuming you're asking. Certainly temperature change is going to be related to types of energy that we use and various types of industry that we use.
Right, that's why I was kind of curious, just because global north versus global south, it's more industrialized in the north, and I was wondering if that was another reason for the disparity.
Oh, yes. I'm going to hold on to that thought for a minute because that's something that I want to come back and talk about a little bit later. Oops. Here we go. All right. So back to ice loss. So we talked about ice area. This next figure here is showing cumulative ice loss and the number of billions of tons of ice that have melted since the mid 1990s. And we can see a very fast rate of increase of ice that we've been losing. The gray shaded area kind of shows you the confidence interval of uncertainty with these values, but we can certainly see even within that confidence range that the quantity of ice loss has been increasing over time, especially with ice that we're losing overland, either from mountain glaciers or from our continental ice sheets. As that ice is melting and that water is making its way down slope toward our oceans, we should expect some amount of sea level rise, and we're already witnessing that. We can use satellite imagery again to monitor sea level rise. Sea level rise is a complicated variable to measure just because there's so much variability with natural wave systems and daily tides and monthly tide systems. But satellites can give us deviations from what we should expect. And we see that trend here in millimeters. This is showing us a rate of sea level rise of about 3.2 millimeters per year in the earlier part of this record. In the last few years of this record, the rate has actually increased a little bit more steeply, closer to about 5 millimeters per year. Doesn't sound like a lot, but there's definitely a lot of regional variability. Some coastlines are seeing sea level impacts already. If you think about places like Miami, Florida, here in the United States. Okay, so those are our major symptoms: warming planet, meaning ice loss, and we've expressed that in a variety of ways. If we look at science of climate change, in a basic physics class, if you take Physics 1 at a university, you're going to learn that all objects emit energy. Everything around you, your body, the table, your computer, your cell phone, your coffee mug, everything is emitting some amount of energy. And the temperature of that object is going to tell us something about the type of energy that that object is emitting. And we can look at the different wavelengths of energy. The visible energy that we see that's primarily emitted from the sun falls within a very narrow range, wavelength between 0.4 and 0.8 micrometers or microns. Most solar energy is visible light that we see. But the sun also emits in smaller quantities other types of energy that you see there along the top, like X-rays, ultraviolet, infrared, microwave, and radio waves. The general rule that the hotter the object is, the shorter the wavelength of energy that it tends to emit. The sun falls within visible energy, so if something was actually hotter than the sun, it would fall somewhere in ultraviolet or X-rays. Cooler objects, like say for example Earth or a human body, we emit our peak amount of radiation within the infrared part of the spectrum. Cooler objects yet would fall even further toward the right-hand side of the figure. The temperature of an object, now this is being expressed in Kelvin temperature, which is essentially Celsius, but you add 273 to the Celsius value so that we can remove the negative part of the Celsius scale. That's essentially all that Kelvin is it's the Celsius scale with no negative values. But as temperature increases, the power that that object emits increases a lot, is the takeaway message of this left-hand figure. There's various types of instruments that we use for monitoring an object's temperature, and often what we're actually measuring is the power that that object is emitting. In the case of the dog over here, this dog is emitting infrared energy. Our instrument measures that amount of infrared energy, and using this relationship, we can convert it to a temperature value. We're doing a lot of that these days with our temperature checks. Every day my toddler goes to daycare, and the first thing they do is check his temperature. We know all of the relationships between the sun and the earth. We have our approximations for the size of both of these objects. We know their approximate distance. They're about 150 million kilometers apart. There is variability in that value throughout the year and over also very long cycles. We know approximately the amount of energy the sun is emitting. It's emitting that energy outwards in all directions, and the Earth captures just a very, very small percentage of that. What we want to now understand is what happens once that energy strikes the top of Earth's atmosphere. So we have a beam of incoming sunlight, here expressed as our bold yellow arrow. Several different things can happen to that energy. Some of it's going to be reflected by the atmosphere, by the gas molecules, the small dust particles, the cloud tops, also by Earth's surface itself. Some of that energy is just reflected simply right back to space again, and that means that we're not going to be using that energy here either in our atmosphere or at our surface. And so we have two arrows representing that reflection. On average, this is going to be about 30% of what has entered the top of the atmosphere. So 30% is lost. Of the remaining 70%, about 20% of that's going to be absorbed by the atmosphere and the clouds. Where that absorption takes place, there'll be some amount of warming in that lower atmosphere. The remaining 50% that we have left, on average, is going to be absorbed by Earth's surface, and it's going to warm the ground. So we have absorption, heating at Earth's surface, by a smaller amount, some absorption and heating of the lower atmosphere, and then the other 30% is lost. So this energy that's been absorbed, Earth's surface, Earth's atmosphere is much, much cooler compared to the sun. So although it's mostly visible energy that's coming in, the energy that Earth's surface and Earth's lower atmosphere is going to be emitting is going to be mostly infrared energy that we're representing as red arrows in this case. Now, why this is a key part of the story is that most of these gases in the atmosphere, specifically the greenhouse gases, which are going to be water vapor, carbon dioxide, methane, nitrous oxide, ozone, and a handful of others, the greenhouse gases are transparent for the most part to the incoming solar energy. They allow that energy to pass through, and that's why that energy is able to be absorbed by Earth's surface. However, the second part of the story is that these gases are not transparent to Earth's outgoing infrared energy. So as Earth's surface and its lower atmosphere is re-emitting energy in the infrared wavelength, most of that is going to be absorbed by the greenhouse gases. And that's going to mean that that energy is going to be held closer to Earth's surface for a longer period of time before it escapes back slowly to space. Think of this in a similar way as you add a blanket on top of your bed during the winter months. Each extra layer of blanket that you add, it's going to maintain some of your body heat closer to your skin and keep you warmer. So each molecule of greenhouse gas warms Earth's surface by a small amount. So let's take a look at the concentration of a couple of these greenhouse gases. We're looking at carbon dioxide here first. If we focus on the top part of the figure, this is the last 10,000 years. We can see that it was fairly steady between 260 and 280 parts per million over thousands of years. And then once we entered that industrial revolution, it's increased at mathematically, it's kind of an exponential rate over the last couple of hundred years. We can focus in on just the last 250 years since 1750, and you can see this a little bit more closely. And if we focus in one more time from the 1950s through the present, using our actual observations from the Mauna Loa observation in Hawaii, the concentration is the black solid line. And we can now see that we're around 400 parts per million here in the present day. You can actually see the intra-annual variability as carbon dioxide is absorbed by plants as they photosynthesize during the warm season months, primarily in the northern hemisphere. And then we see the values increase as photosynthesis decreases over the cold season months. So the black line is what we actually measure for carbon dioxide in the atmosphere. The gray line is actually the carbon dioxide emitted into the atmosphere each year. It's approximately double what we actually measure. Now, the reason why the concentration is only about half is because photosynthesis is taking place, so there's some absorption by trees and plants, but the oceans are also absorbing much of the carbon dioxide that's in the atmosphere. So the good news here is that the planet does have some natural methods of removing some of this carbon dioxide from the atmosphere, about half. Methane is CH4. It also contains carbon. Its story is very similar. Over the last 10,000 years, we can see exponential growth here, closely related to the Industrial Revolution. You can see that in the inset part of the figure here. If you're not already familiar with that, carbon dioxide is primarily emitted from fossil fuel combustion, specifically from coal-fired power plants. Methane is emitted in a variety of different ways. It's emitted through various types of agriculture, like livestock, rice farming, decomposition. And so one of the things that we're concerned about as scientists right now is as permafrost thaws, this is going to be a source for methane emission in years going forward. Okay, so next I want to summarize what we consider 5 forcings of climate change. So these are things that are going to alter Earth's system and probably have a variety of consequences once one of these is set in motion. And so I've summarized these in 5 categories. The first is geologic. So this is going to include anything from climate change that results from continental drift or plate tectonics. So as the land masses actually physically move across Earth's surface, climates are going to change. It could be from volcanic activity. It can also be from impacts from extraterrestrial bodies, comets, asteroids, and anything smaller. I mean, a lot of these are going to be catastrophic types of events if they're of an impact. We also have solar climate forcings. So this can be in regards to the actual output of solar energy varying over time. This is very closely related to the 11-year sunspot cycle, and we've captured 3 of those here in recent years. If we look at solar output throughout its lifetime, solar output should be increasing, although there is variability from year to year and decade and century and millennia. In fact, in recent decades, we're seeing solar output actually on the decline as Earth's temperatures have been increasing. So that leads us to believe that solar output is not the leading cause for warming temperatures we've seen over the last several decades. There are thousands of year cycles that relate to the axial tilt of Earth's surface, and also thousands of year cycles that relate to the shape of Earth's orbit. The orbit is not a perfect circle, it's more of an ellipse, and that ellipse does change in its eccentricity over time. It takes about 100,000 years to repeat that cycle. So that cycle can help us understand climate change over very long periods of time. That's not going to give us much understanding of rapid temperature change on the order of decades. Same with the axial tilt cycle. That one's about 41,000 years to complete that. Over Earth's history, it is very closely related to our periods of glacial advance and retreat. But again, it's not going to help us understand warming temperatures over a short time period. Earth certainly undergoes variability in its atmospheric and oceanic circulation. Most of this is internal variability, thinking about things like El Nino, La Nina in the Pacific Ocean. This helps us understand temperature variation on a global scale from month to month and from year to year, and sometimes even on a decadal scale. But for the most part, doesn't help us understand global climate change. There are some examples of where disruptions in atmospheric and oceanic circulation can create um, abrupt climate change. And an example might be like a large continental ice sheet falling off into the ocean, as one large chunk of ice and disrupting oceanic temperature and oceanic circulation. There are some pieces of evidence that suggest that's happened in Earth's history. Finally brings us to human activities. Our main contributions are our ability to alter the landscape. That's going to affect then the amount of absorption and reflection of energy. Thinking about how we can deforest an area or reforest it. We can change forest to agriculture. We can change agriculture to a new suburb. We can change a suburb to a new urban area. There's a variety of different ways that we can alter the landscape. And each one of these is going to affect the previous amount of absorption versus reflection. Okay, so to complicate these climate change forcings a little bit more, our system also has feedback mechanisms that can and do occur. And these feedbacks can exacerbate a current amount of change. So I've illustrated one example of a feedback. There are many of these, but before I get to this example, I just want you to kind of picture in your head the domino effect, where you stand up all of the dominoes, one after the other. And so that's our system. We have a system of dominoes. And then someone comes along and they knock over that first domino. So it's a very small initial change. But of course, once that first domino has fallen over, it's going to make an impact with its neighbor, and then it's going to impact its neighbor, and suddenly it becomes a self-sustaining change. And the change exaggerates down the line until probably all the dominoes fall over. So that's a simple example of a feedback. Another example that we are observing is what's referred to as the ice reflectivity feedback. And so someone was asking earlier about the ratio or the difference between the northern and southern hemisphere and the amount of change of warming. And so with more industry in the northern hemisphere, with more fossil fuel combustion in the northern hemisphere, with more deforestation, more wildfire, and more volcanic activity in the northern hemisphere, since where most of the land mass is, that's where most of the people are, there's more greenhouse gas emission in the northern hemisphere. So more greenhouse gas emissions here means a greater greenhouse effect in the northern hemisphere, which means a greater amount of warming in our hemisphere. So that provides our initial warming. That's the initial domino that gets knocked over, is that small warming to start the chain reaction. So in our hemisphere, as the atmosphere warms, it's going to mean ice melt in the Arctic Circle. As that ice melts, it's going to change the reflectivity, because whether it's sea ice and we have now fresh ocean that's going to be exposed, or we have ice that melts over land and then we have new land that's exposed, usually it means that the reflectivity of whether it's the water or land surface, the reflectivity is going to decrease and the absorption is going to go up. So it's going to mean more absorption at Earth's surface, more warming of that surface, which is then going to accelerate further ice melt. And you can see that we've now created this closed feedback loop that's going to exaggerate more melting, more warming, more melting, more warming. And this is what we believe is occurring currently in the Arctic Circle, and why we're seeing warming occurring so rapidly and ice melt occurring so rapidly in the Arctic Circle in particular. This is just one example. There are probably dozens of feedbacks. Some of these have to do with clouds. Some of them have to do with um, the amount of energy that Earth is emitting. Fortunately, there are some feedbacks that counterbalance this, so it allows this runaway system to not dominate what happens. All right, so I'm just going to check the chat box here. Someone says, do you know if more methane is produced by rice farming or livestock raising? That is a good question. I don't know the actual numbers. Both are measurable. I'm not personally aware of what the numbers are, and I don't know if either of those is the leading cause. Perhaps permafrost thaw is going to be what's most dominant in the decades to come. Um, there's a lot of interesting sources of methane emission. Um, it's very closely related to natural gas extraction and use as well, and we're becoming increasingly more reliant on natural gas as a fuel source. So that's another important place of where methane is emitted. Even termites emit methane from their termite mounds, so that's another important source that we have very little control over. All right, so next figure, let's focus on the top part of this first. The gray line, you've seen this in a different version before. This is showing Earth's global average temperature again, that increase in the early part of the 20th century, stagnant temperatures in the mid-20th century, and then warming since that time. What we've added to the figure now is we're now looking at global circulation models, or GCMs. And when we are creating the code and the calculations that goes into that code for those models, the best practice is to run it against historic records of temperature first, so that way we can compare it to actual observations and see how well the model performs. So taking our understanding of physics of these natural climate forcing, so things like changes in the solar energy, volcanic activity, changes in the relationship between the sun and the earth, changes in atmospheric and oceanic circulation, if we include only those calculations in the models, and this is not just from one model, this is from more than a dozen different models, and look and averaging the results. If we look at just natural climate forcings, that gives us a temperature illustrated by the solid black line. And you can see that it does okay in the first half of the 20th century, but after the mid part of the 20th century, there's a clear divergence between what the models were suggesting and what the actual observations of temperature ended up being. It suggests, if anything, in the second half of the 20th century that there should have been declining temperatures on a global scale. So certainly not what we have experienced. That brings us to the second part of the figure. If we take the same models and then include the information that we understand in regards to human activity and how we contribute, so things like land cover change, greenhouse gas emissions, we run the models again, and now we get much better agreement, especially in the last several decades. It's not a perfect fit, but you can see it gives us the overall trend. The model represents the 20th century pretty well, and it gives us a strong confidence that if we run the models in the future, that it's also going to give us a pretty good representation. Nothing perfect, but it gives us a ballpark idea, which is what we're trying to accomplish. Okay, so it brings us to our final portion for today on solutions. And I want to start this by looking at the challenge that us climate scientists are up against, or scientists in general, really. Certainly on a societal scale here in the United States, there is general pushback against science. We're seeing this pretty much daily in the news. If you just follow what's going on with Anthony Fauci and the other leading pandemic scientists right now, there's a lot of controversy that really shouldn't be there, in my personal opinion. And that's front and center in the media, so we can see that. but just know that it occurs in a lot of different avenues within science, and certainly climate science is an area considered to be controversial. To me, it's not controversial at all. The science is pretty unequivocal, and clear to me. Um, but there's three major pushbacks that we receive, and it comes in one of these three forms or some combination of these. It can be a science rebuttal saying that climate change is entirely natural. My response to that is that climate change has occurred naturally. That is true, and most climate change has occurred from natural cycles. But the last figure that I showed you, where we used the climate models, we saw that natural forcings alone cannot explain climate change since about the 1970s through the present. That is kind of the smoking gun for us climate scientists, that to us, without a doubt, since the 1970s through the present, humanity has really been the leading forcing for the climate change that we've experienced. It becomes less certain if we're looking further back in time, but over the last several decades, everything the evidence suggests that human emissions of greenhouse gases is what's responsible for recent warming. Second argument is a religious-based one. For folks who hold religion in high regard in their life, it's hard to argue that point with them. I would just simply say that regardless of your religious background, most religious entities still provide some amount of free will, and our decisions that we make, we do have to live with those consequences. So even if your belief system is that God is, or some other religious entity is in control, usually there's still room for your own decision making, and there are going to be consequences of those decisions. The final argument is economic based, and it might be that changing our energy system is going to be expensive. My rebuttal to that is that any energy system is expensive. Currently, we heavily subsidize our fossil fuel sources of energy. Really, all it takes is the desire and the will to move those tax subsidies from the traditional sources of energy like coal, natural gas, and oil, move those subsidies toward renewable sources of energy like wind and solar. Common strategy that you will encounter, and this can come from either side of the climate change argument. I always caution readers to pay attention to what you're being shown and also what you're not being shown. A climate change advocate might show you this time series of temperature. Let's not pay attention to the bold lines here first. Just pay attention to the thinner gray line. Climate change advocate may show you just the temperature since 1970. You've seen this in various forms several times today. You know that temperatures have increased since the 1970s. So this kind of pinpoints that upward trend. It removes some of the other trends that occurred earlier in the record. Personally, I prefer to show you as much information as possible so you can see the whole picture. To only show from 1970 to the present is a biased depiction. Further, a climate change skeptic might show you the same record, but then try to zero in on specific dates where the trend actually decreases. And we've picked out 7 examples of that shown by the black solid lines. Notice how each one of those is declining. Notice that they're very short time periods too, on the order of just a few years in order to create those. This is one of the reasons why climate scientists don't focus on short periods of record, because there's just so much regular year-to-year variability. There are always going to be some cool days, months, and years. When we think about climate change, we need to be thinking about on the order of decades or longer. Usually the bare minimum is 3 decades or 30 years. If you have an even longer time period, it's all the better. So looking at climate modeling just a little bit, these are 4 different scenarios. And we use scenarios because we don't yet know what the future holds. We don't know exactly what types of energy we'll use, what the emissions will be, what the human population will be. We can provide our best guesses, and so we've created 4 different scenarios. RCP stands for Representative Concentration Pathway, and then the numeric value has to do with the energy that has been increased in Earth's atmosphere system. The lower the value means the less energy. This type of scenario is going to mean a more rapid change over to renewable energy, more action in regards to population control. You can see that these are emissions of carbon and how it peaks and then rapidly decreases to actually negative carbon emissions by the end of this century. So this would be rapid, dramatic changes in our society to accomplish that scenario. The bold line, you can kind of think of that as our business as usual. This is the trajectory that we've been on in recent years, and if we follow that trend, we continue to rely on fossil fuels, population rates of growth don't change that much, we'll follow that line. And then we have a couple more intermediate scenarios. Now, you know that the emissions, from what we learned today, about half of that's going to be absorbed by the oceans and by plants through photosynthesis. So the actual concentration in the atmosphere in parts per million is going to be this figure. Again, the business as usual is the black solid line. That's the trajectory that we are on. Today we're around 410 to 415 parts per million. Then we have the other scenarios. I can tell you that recent research that's come out since these figures were created are suggesting that the 2.6 and the 4.5 scenarios are becoming less and less feasible as the years go on. The RCP 6 or 8.5 are more realistic based on the trajectories that we've been following. Now, carbon dioxide, how that relates to global temperature brings us to this figure. Business as usual against the solid line. In terms of our realistic goals, we're probably going to fall somewhere in the middle of this figure, hopefully. And we can see by the end of the century, it's going to result in a global temperature increase on the order of 2 to 3 Celsius, but the overall range between all 4 of these scenarios is 1 to 4 degrees Celsius. That's why you'll see those values in the media and in publications frequently. Doesn't sound like a lot, and it is on the Celsius scale, but just keep in mind that Earth's average temperature change between glacial advance and glacial retreat has been on the order of only about 5 degrees Celsius or so. And those changes in temperature historically have occurred over thousands of years. We're going to be accomplishing that rate of change in a century. 1 century. The rate of change is what has scientists concerned because plants and animals may not have the time to adapt within such a short window. These are really our 3 strategies going forward. We can choose to adapt to climate change. Climate change is already here. Impacts are already being felt. An example of adaptation would be running your air conditioner more in the summer months. Communities using infrastructure to defend themselves against sea level rise in coastal areas. Those are examples of adaptation. Mitigation are strategies of trying to decrease our impact on climate change. So this would be changing our energy sources away from fossil fuels toward renewable energy so that we are actively decreasing the greenhouse gas emissions that we're producing. Finally, we can geoengineer. And geoengineer comes in really 2 main categories. We can try to create technology which affects the amount of solar energy that's actually absorbed by Earth's surface. There's a variety of ways that we can accomplish that. We can either directly try to change Earth's surface so that we affect the amount of reflection versus absorption, or we can try to um, insert material into the atmosphere itself so that we're able to block that sunlight from ever reaching Earth's surface in the first place. The other method of geoengineering would be to actively try to remove greenhouse gases from the atmosphere. So that would be what's referred to as carbon sequestration. Now, it's probably going to take a combination of these three strategies to be successful. I want to show you that our mitigation strategies actually have already had success. This figure shows us 4 different variables and how they relate to carbon dioxide impact in the atmosphere. We have Earth's population as the solid line. These values are relative to their value in 1970. Population has increased steadily. Now, fertility rates are declining worldwide, but the fact that there's so many of us on Earth's surface and life expectancy has generally increased with time. These things have kind of built in population growth that's going to continue throughout this century, really regardless of no matter what we do. Even in the face of a pandemic, global population is going to increase throughout that. So there's very little we can do to change the population line. In terms of trying to combat poverty, we're going to want to see income per person stay steady with population. That's the plus signs here. This is expressed as, or excuse me, population was the plus sign. Income or GDP per person is the solid black line, but you can see they're very closely tied together. And if we want income per person to stay steady with population, we're not going to affect the GDP. So there's very little that's going to happen with those two. We're going to continue to see those go up. But the other two terms, the dotted line and the dashed line, these have to do with our energy use, our consumption, the types of energy that we're using, and mitigation strategies that are tied to that. The dotted line is carbon intensity, and its units are carbon dioxide per joule. So this is very closely related to energy efficiency. For each joule of energy we consume, how much greenhouse gas is emitted? And you can see that this has decreased, which shows that efficiency has gone up since 1970. The dashed line is showing energy intensity, and this is joules per dollar spent. So this is showing us that we're getting more energy for each dollar that we're spending as we've gone through time. Both of these tell us something about our energy use and its efficiency. And it's really in regards to mitigation strategies. And as we continue to add more mitigation strategies, we should see these values continue to decrease over time. Okay, so my final point to leave you with today is I'm probably preaching to the choir because you've devoted your last hour to listen to me today, but I hope that this will inspire you to continue to want to learn more about climate change. But secondly, I hope that this inspires you to want to talk with your friends and family, those around you, about what you've learned today and what you understand about climate change. I think climate change communication is the most important weapon that we have of trying to get other people to understand the story and why it's important. The other thing we can certainly do, most of us just did this about a week ago, is get to the polls and vote for candidates at all levels, local, state, and federal levels, the candidates that support environmental protection and strategies toward adaptation, mitigation, and geoengineering. All right, and with that, I will take a look at the chat box again.